Hello, I'm Selin, and in this video we are going to cover vehicle routing problem. First of all, what is VRP? It's a classic optimization challenge in logistic and operations research. At its very core, it asks this question: what is the most efficient set of routes for a fleet of vehicles to deliver goods or services to a specific set of customers? It's considered as a generalization of the traveling salesperson problem. TSP focuses on one person visiting multiple locations, whereas VRP manages multiple vehicles departing from one or more depots. The goal of VRP is to minimize the total cost of delivery while satisfying various constraints. These costs are usually measured in terms of total distance traveled, number of vehicles used, or total travel time. VRP is used for route planning and optimization in various contexts. For example, delivering goods in logistic networks, or scheduling service or delivery vehicles. But sometimes even non-vehicle tasks like scheduling and circuit design. There are different types of VRPs. I'm going to talk about three of them. First one is vehicle routing problem with time window. In this specific type of VRP, the vehicle must deliver the product to each customer within a specific time window, or there will be a specific servicing time allocated for each customer. The second one is capacitated vehicle routing problem. Here, vehicle capacity is an important factor to consider while deciding the route to be taken. The capacity of vehicles may be limited and they are out of serve customers with known demands. The third one is vehicle routing problem with pickup and delivery. This type of problem exists when the fleet driver handles both pickup and delivery consequently. In order to understand VRP, let's talk about the components of it. Fleet, different types of vehicles, their specialties and capacities, fuel cost, etc. Customer demands, the location of end users, their requirements, required quantities, delivery expectations, and etc. Routes that the delivery personnel must take, covering deliveries as a one-way trip or returning to the start point. And other considerations can be classified as weather changes, driving working hours, or special storage requirements like refrigeration, etc. Common constraints are capacity, load balance, time windows, vehicle types, and driver limits. You will understand everything better when we solve an example. We have an example problem. The Artisan Roast delivery. A central coffee roaster delivers fresh beans to 4 cafes. The operation uses 2 identical delivery bikes, each with a maximum capacity of 15 kilograms. The goal is to minimize the total distance while meeting all demand. As you can see, here is the customer demands. Coffee 1 demands 5 kilograms of coffee. Coffee 2 demands 7 kilograms. And coffee 3 demands 4 kilograms. And coffee 4 demands 6 kilograms. This is our distance matrix. It shows the distance between each node. As you can see, the distance between node 1 to node 2 is 5. And you see these big numbers in the diagonal elements of the distance matrix. They are called penalty value. They are used to prevent the model from selecting self-loops, effectively simulating an infinite distance for prohibited transitions. Let's move on to the mathematical model. First of all, we define indices and sets. Ij, set of all nodes where V is 0, 1, 2, 3, and 4. Node 0 is a depot. This is where we are going to come back to. This is our roastery. K is the set of vehicles where K is vehicle 1 and vehicle 2. And C is set of our customers where again 1, 2, 3, and 4 because we have 4 cafes. Let's talk about parameters. Mij is the distance between node A and node J as can be seen in the distance matrix here. And DI is demand of customer in kilograms here again. Q is maximum capacity of each vehicle. In this specific problem, it's 15 kilograms. And N is again for number of customers. These are our decision variables. X, I, J, K equals to 1 if vehicle K travels from node I to node J. 0 is otherwise. Auxiliary continuous variable. It's used for subtour elimination. It represents the visit sequence of vehicle K at customer A. And Z is total distance traveled. This is going to be our objective value. So the objective function is that minimizing the total distance traveled by all vehicles. Here you can see the equation. Here we multiply the distances by the decision variable. Here are constraints. First constraint that we are going to talk about is customer coverage. Each customer must be visited exactly once. Here is the constraint for it in mathematical form. And flow conservation. If a vehicle enters a customer node, it must leave it. It can't stay there forever. The mathematical expression for it is here. Depot departure. Each vehicle can leave the depot at most once. And depot return. Each vehicle must return to the depot at most once. All these constraints are actually about the fact that you can visit a node only once and leave it only once, and you return to your depot node. All the constraints are essentially about that. Here we have the capacity constraint. Total demand carried by vehicle K cannot exceed Q. In this question it was 15. This is the mathematical form of it. And subtour elimination constraint. Prevent cycle that do not include the depot. This is extremely important in VRP, as we talked before. We don't want subtours, we don't want loops, we just want to visit one node exactly once, and we are going to cover all the nodes, and then we are going to go back to our depot node. So we also have binary routing decisions and positive auxiliary variables for subtours. As you can see, x, I, j, k can only be 0 or 1 because it's binary. And here's the auxiliary variable constraint. Solving the model. A video showing how I solve this model using GAMS is linked in the description. I won't be solving it in this video, but please make sure to watch it as well so you can see the solution for this and the objective function value and which nodes are visited by which vehicle. In conclusion, the vehicle routing problem is a critical tool for optimizing logistics and reducing operational costs. By integrating capacity constraints and subtour elimination, our model effectively balances customer demands with vehicle limits to ensure the most efficient delivery paths. Thank you so much for listening, and please tune in for our other videos so you can learn more about location selection and facility planning and operations research. Thank you.